Good morning, everyone. Welcome to the Basic Education Math Teacher Society webinar series. Today is day 1, October 9, 2021. And our topic is all about Introduction to Factor Analysis. I am Dr. Craig and Refugio. I am from Negros Oriental State University, Main Campus 1, Dumaguete City. In my talk, I'll be talking about the basic concepts of factor analysis, and I will be giving common examples, practical examples of factor analysis. What is a factor analysis? According to Adelman and Morris way back 1991, factor analysis is a way to condense the data in many variables into a just few variables. For this reason, it is also sometimes called dimension reduction. You can reduce the dimensions of your data into one or more super variables. The most common technique is known as principal component analysis, or PCA. How factor analysis can help researchers? Factor analysis is useful in, number 1, condensing variables. There are many variables at the very beginning, and the purpose of the researcher is to condense, to reduce those many variables into fewer variables. Number 2, uncovering clusters of responses. There are many variables. It would follow that there are also many responses. And from the many responses, they will be clustered into clusters with commonalities among responses. Number 3, providing simplicity after reducing variables. Since there are many variables and they're being reduced into fewer variables, thus those fewer variables can be classified as a simple set of variables. So you ask several questions, all driving at different but closely related aspects of customer satisfaction. Number 1, how satisfied are you with our product? Number 2, would you recommend our product to a friend or family member? Number 3, would you likely purchase our product in the future? But you only want one variable to represent a customer satisfaction score. One option would be to average the 3 question responses. Another option would be to create a factor-dependent variable. This can be done by running PCA and keeping the first principal component, also known as a factor. The advantage of PCA over an average is that it automatically weights each of the variables in the calculation. Say you have a list of questions and you don't know exactly which responses will move together and which will move differently. For example, purchase barriers of potential customers. The following are possible barriers to purchase. Number 1, price is prohibitive. Number 2, overall implementation cost. Number 3, we can't reach a consensus in our organization. Number 4, product is not consistent with our business strategy. Number 5, I need to develop an ROI, but cannot or have not. Number 6, we are locked into a contract with another product. Number 7, the product benefits don't outweigh the cost. Number 8, we have no reason to switch. Number 9, our IT department cannot support your product. Number 10, we do not have sufficient technical resources. Number 11, your product does not have a feature we require. Number 12, other, please specify. Factor analysis can uncover the trends of how these questions will move together. The following are loadings for 3 factors for each of the variables. So it is assumed that this set of instrument is actually being administered. The responses are loaded to a software, and is the outcome, the output from the software. So we have PC1, PC2, PC3. And we have the following questions. Price is prohibitive. Overall implementation cost. We can't reach consensus in our organization. So forth and so on up to other please specify. So under PC1, so we have 0.49, 0.41, and 0.68 as weights that actually meet with the requirements. Some authors would say at least 0.40, but different authors, different statisticians, different literature have different standards, and I will be talking about it later. PC2, we have 0.30, negative 0.77, 0.38, then 0.58, and we also have 0.38. PC3, we have 0.57, 0.45, 0.62. Notice how each of the principal components have high weights for a subset of the variables. The first component, as you see, PC1, or the first component, heavily weights variables related to cost. So we have price is prohibitive, overall implementation cost, and we have the product benefits don't outweigh the cost. So all of these items are actually referring to cost. So the general term labeled for these different statements are considered as cost. The second component, PC2, weights variables related to IT. So we have no reason to switch. Our IT department cannot support your product. We do not have sufficient technical resources. The third weights variables related to organizational factors. So we can give our new super variables clever names. So we can actually provide name of those factors being clustered together. And in some cases, it's actually the most difficult part because we have to research, we have to think it logically on what would be the exact name for this cluster of statements. So we have the product benefits don't outweigh the cost. The price is prohibitive. Overall implementation cost. We do not have sufficient technical resources. Our IT department cannot support your product. Product is not consistent with our business strategy. We can't reach a consensus in our organization. I need to develop an ROI but cannot or have not. Your product does not have a feature we require. We're locked into a contract with another product. Others, please specify. We have no reason to switch. So we have cost, we have IT, and we have organization. So for organization, we have the weights 0.45, 0.57, 0.62. For IT, we have 0.38, 0.58, 0.38, then negative 0.77. And for cost, we have 0.68, 0.49, 0.41. If we were to cluster the customers based on these three components, we can see some trends. Customers tend to be high in cost barriers or organization barriers, but not both. Looking at this scatter diagram, the x-axis, we have the cost barrier. The y-axis is all about organizational barrier, looking into two-dimensional factors. Factor analysis according to Hatcher, 1991. Factor analysis is a method for modeling observed variables and their covariance structure in terms of a smaller number of underlying unobservable latent factors. The factors typically are viewed as broad concepts or ideas that may be described unobserved phenomenon. For example, a basic desire of obtaining a certain social level might explain most consumption behavior. These unobserved factors are more interesting to the social scientists than the observed quantitative measurements. Factor analysis is generally an exploratory descriptive method that requires many subjective judgments. It is a widely used tool and often controversial because the models, methods, and subjectivity are so flexible that debates about interpretations can occur. The method is similar to principal components, although, as the textbook points out, factor analysis is more elaborate. In one sense, factor analysis is an inversion of principal components. In factor analysis, we model the observed variables as linear functions of the factors. In principal components, we create new variables that are linear combinations of the observed variables. In both PCA and FA, the dimension of the data is reduced. Recall that in PCA, the interpretation of the principal components is often not very clean. A particular variable may, on occasion, contribute significantly to more than one of the components. Ideally, we like each variable to contribute significantly to only one component. A technique called factor rotation is employed towards that goal. Examples of fields where factor analysis is involved include physiology, health, intelligence, sociology, and sometimes ecology, among others. So why do we use factor analysis? So factor analysis, according to Hackett way back 1986, is a useful tool for investigating variable relationships for complex concepts such as socioeconomic status, dietary patterns, or psychological scales. It allows researchers to investigate concepts that are not easily measured directly by collapsing a large number of variables into a few interpretable underlying factors. So what is a factor? The key concept of factor analysis is that multiple observed variables have similar patterns of responses because they are all associated with latent, that is, not directly measured variable. For example, people may respond similarly to questions about income, education, and occupation, which are all associated with the latent variable socioeconomic status. In every factor analysis, there are the same number of factors as there are variables. Each factor captures certain amount of the overall variance in the observed variables. And the factors are always listed in order of how much variation they explain. The eigenvalue is a measure of how much of the variance of the observed variables a factor explains. Any factor with an eigenvalue greater than or equal to 1 explains more variance than a single factor variable. So if the factor for socioeconomic status had an eigenvalue of 2.3, it would explain as much variance as 2.3 of the 3 variables. This factor captures most of the variance in those 3 variables, could then be used in other analyses. The factors that explain the least amount of variance are generally discarded. So what happened to this table? Go back to this table. Those very, very small numerical values are actually being discarded. What are factor loadings? So we'll be talking also about factor loadings as terms in factor analysis. According to RAN 2001, the relationship of each variable to the underlying factor is expressed by the so-called factor loading. Here's an example of the output of a simple factor analysis looking at indicators of wealth with just 6 variables and 2 resulting factors. So first column variables. So the variables are income, education, occupation, house value, number of public parks in neighborhood, number of violent crimes per year in neighborhood. Factor 1, we have 0.65, 0.59, 0.48, 0.38. We have 0.13, we have 0.23. Factor 2, we have 0.11, 0.25, 0.19, 0.60, 0.57, 0.55. So if you notice, the highlighted one are actually those having acceptable values. Some would say at least 0.4, some would say at least 0.3, depending on the authority that you're actually citing. So 0.13, 0.23 are not being considered. 0.11 and 0.25 are not also being considered. The variable with the strongest association to the underlying latent variable, as you see in the table, factor 1 is income, with a factor loading of 0.65. Since factor loadings can be interpreted like standardized regression coefficients, one could also say that the variable income has a correlation of 0.65 with factor 1. This would be considered a strong association for a factor analysis in most research fields. Two other variables, education and occupation, are also associated with factor 1. So we look at factor 1, income, education, occupation, and house value. Based on the variables loading highly onto factor 1, we could call it individual socioeconomic status. The term individual socioeconomic status is actually a name created for income, education, occupation, and then house value. House value, number of public parks, a number of violent crimes per year, however, have high factor loadings on the other factor, factor 2. They seem to indicate the overall wealth within the neighborhood. So we may want to call factor 2 as neighborhood socioeconomic status. We look at factor 2. We look at number of public parks in neighborhood, number of violent crimes per year in neighborhood. If you notice, there's actually an overlap, house value for factor 1 and factor 2, but it has a greater factor loading for factor 2. So house value would belong to factor 2. Notice that the variable house value also is marginally important in factor 1. The loading is 0.38. And this makes sense since the value of a person's house should be associated with his or her income. So factor in factor analysis. So what do we mean by factor or factors in factor analysis? According to Martin and Osborne way back 2000, in factor analysis, a factor is a latent, unmeasured variable that expresses itself through its relationship with other measured variables. Take, for example, a variable like leadership. We may want to measure a person's or an organization's leadership style, but this is the kind of construct that would be impossible to measure using a single variable. It is just too abstract and multifaceted, although it does represent a single concept. So instead, you may have to develop the scale with many items, each of which measures some more measurable part of leadership. The idea would be there is an underlying unmeasurable factor, leadership, that causes people to respond in certain patterns on the many items on the scale. The purpose of factor analysis is to analyze these patterns of response as a way of getting at this underlying factor. Factor analysis also allows you to use the weighted item responses to create what are called factor scores. These represent a single score for each person on the factor. Factor scores are nice because they allow you to use single variable as a measure of the factor in the other analysis rather than a set of items. How big a sample size do you need for a factor analysis? According to Martin and Harrington way back 1999, most of the time when we plan a sample size for a data set, it is based on obtaining a reasonable statistical power for a key analysis of that data set. These power calculations figure out how big a sample you need so that a certain weight of a confidence interval or p-value will coincide with a scientifically meaningful effect size. But that is not the only issue in sample size, and not every statistical analysis uses p-values. One example is factor analysis. A factor analysis is a measurement model of an underlying construct. So like regression models, structural equation models, and latent class models, the focus is on understanding the structure of the relationships among variables. The specific focus in factor analysis is understanding which variables are associated with which latent constructs. The approach is slightly different if you are running an exploratory or confirmatory model, but the overall focus is the same. If a power is not the main issue, how big a sample do you need in factor analysis? The long answer is a little more complicated, mainly because there is not one right answer. Authors have differing opinions on exactly how many subjects you need and on exactly which criterion to use. However, we have rules of thumb. For example, some authors use a criterion based on the total sample size. 100 subjects equals sufficient if clear structure, more is better. According to Klein, 1994. 100 subjects equals poor, 300 equals good, 1,000 plus equals excellent. Combre and Lee, 1992. 300 subjects, though fewer works if correlations are high among variables. Tabachnik and Fidel, 2001. Others base it on a ratio of the number of cases to the number of variables involved in the factor analysis. 10 to 15 subjects per variable, Pett, Lucky, and Sullivan. 10 subjects per variable, Nunnally, 1978. 5 subjects per variable, or 100 subjects, whichever is larger, Hatcher, 1994. 2 subjects per variable, Klein, 1994, and then others base it on a ratio of cases to the number of factors. 20 subjects per factor, Arindale and van der Ende, 1985. Here are a few takeaways. Number 1, you're going to need a large sample. That means in the hundreds of cases, more is better. Number 2, you can get away with fewer observations if the data are well behaved. If there are no missing data and each variable highly loads on a single factor and not others, you won't need as many cases. But counting on the data behaving is likely counting on the weather behaving during hurricane season. You will have a better outcome most of the time if you plan for the worst. Number 3, the main issue with small data sets is overfitting. A secondary issue is if the sample is really small, the model won't even converge. It is a simple concept. When a sample is too small, you can't get what looks like good results, but you can't replicate those results in another sample from the same population. All the parameter estimates are so customized to this particular sample that they are not useful for any other sample. This can and does happen in any model, not just factor analysis. All the parameter estimates are so customized to this particular sample that they are not useful for any other sample. This can and does happen in any model, not just factor analysis. Yes, confirmatory factor analysis can use p-values for overall model fit, chi-square test, as well as specific path coefficients. Exploratory factor analysis does not. So when are factor loadings not strong enough? But earlier I mentioned about factor loading. So when can we say that factor loadings are not actually strong enough? According to RAN 2001, once you run a factor analysis and think you have some usable results, it's time to eliminate variables that are not strong enough. They are usually the ones with low factor loadings, although additional criteria should be considered before taking out a variable. As a rule of thumb, your variable should have a rotated factor loading of at least absolute value of 0.4, meaning greater than plus 0.4 or less than or equal to negative 0.4 onto one of the factors in order to be considered important. Some researchers use much more stringent criteria, such as cutoff is absolute value of 0.7. In some instances, this may not be realistic. For example, when the highest loading a researcher finds in analysis is absolute value of 0.5. Other researchers relax the criteria to the point where they include variables with factor loadings of absolute value of 0.2. Which cutoffs to use depends on whether you are running a confirmatory or exploratory factor analysis, and on what is usually considered an acceptable cutoff in your field. In addition, a variable should ideally only load cleanly onto one another. So based on this concept, when our factors loadings not strong enough, we have to read different literature and then always cite our basis of considering acceptable loadings. How many variables and observations? According to RAN 2001, another question often asked is how many variables a researcher should use for analysis. Generally, each factor should have at least 3 variables with high loadings. It is also important to have sufficient number of observations to support your factor analysis. Per variable, you should ideally have about 20 observations in the data set to ensure stable results. A common minimum is the lesser of 10 observations per variable and 100 observations. However, some statisticians would go as low as 5 observations per variable. Next is the concept on rotations as one of the terms of factor analysis. According to RAN 2001, an important feature of factor analysis is that the axis of the factors can be rotated within the multidimensional variable space. What does that mean? Here is, in simple terms, what a factor analysis program does while determining the best fit between the variables and the latent factors. Imagine you have 10 variables that go into a factor analysis. The program looks first for the strongest correlation between variables and the latent factor and makes that factor 1. Visually, one can think of it as an axis, axis 1. The factor analysis program then looks for the second set of correlations and calls it factor 2 and so on. Sometimes the initial solution results in strong correlation of a variable with several factors or in a variable that has no strong correlation with any of the factors. In order to make the location of the axis fit the actual location of the data points better, the program can rotate the axis. Ideally, the rotation will make the factors more easily interpretable. Here is a visual of what happens during a rotation when you only have two dimensions, x and y axis. So here's the figure. The original x and y axis are colored in black. During the rotation, the axis moved to a position that encompasses the actual data points better overall. Programs offer many different types of rotation. An important difference between them is that they can create factors that are correlated or uncorrelated with each other. So take note that an important difference between them is that they can create factors that are correlated factors or uncorrelated factors to each other. Rotations that allow for correlation are called oblique rotations. Rotations that assume the factors are not correlated are called orthogonal rotations. Our graph shows an orthogonal rotation. Once again, let's explore indicators of will. Let us imagine the orthogonal rotation did not work out as well as previously shown. Instead, we get this result. Variables. So, income, education, occupation, house value, number of public parks in neighborhood, number of violent crimes. Factor 1, 0.63, 0.47, 0.45, 0.39, 0.12, 0.21. Factor 2, 0.14, 0.24, 0.22, 0.25, 0.20, and 0.18. So based on the table, clearly no variable is loading highly onto factor 2. If you notice 0.14, 0.24, 0.22, 0.25, 0.20, 0.18 are actually lower than 0.4. We base our standard as acceptable loading would be at least 0.4. Since our first attempt was an orthogonal rotation, we specify that factor 1 and factor 2 are not correlated. But it makes sense to assume that a person with high individual socioeconomic status, factor 1, lives also in an area that has a high neighborhood socioeconomic status. Factor 2. That means factors should be correlated. If you look at factor 1, 0.63, 0.48, 0.45, 0.39. Consequently, the two axes of the two factors are probably closer together than an orthogonal rotation can make them. Here's a display of the oblique rotation of the axis of our new example, in which factors are correlated with each other. Clearly, the angle between the two factors is now smaller than 90 degrees, meaning the factors are now correlated. In this example, an oblique rotation accommodates the data better than an orthogonal rotation. So how to reduce the number of variables to analyze? According to Ran and Giannoli's way back 2001, many data sets contain well over 1,000 variables. Such complexity, the speed of contemporary desktop computers, and the ease of use of statistical analysis packages can encourage ill-directed analysis. It is easy to generate a vast array of poor results by throwing everything into your software and waiting to see what turns up. So why do variables need to be selected before analyzing the data? According to Ron and Genolis, way back 2001, the thoughtless analysis of data is a problem for a number of reasons. It is easy to consider into a data analysis without even thinking about what the intended endpoints are. Analysis without thinking will almost certainly produce biased results. Powerful multivariable techniques such as multiple regression make it easy to include a very large number of predictor variables in the hope of maximizing the explanatory power of the model. A similar problem occurs with factor analysis. There is nothing stopping us from factor analyzing a random set of variables. Factor analysis will nearly always produce a solution. However, it may well be a nonsense solution. Factor analysis is designed to identify sets of variables that are tapping the same underlying phenomenon. It does this by examining the patterns of correlations among a set of variables. The assumption of factor analysis is that the variables that are identified as belonging to a factor are really measuring the same thing. The factor itself is driving the responses on the individual variables. Therefore, they should not be causally related to each other. Unfortunately, factor analysis cannot distinguish between variables that are causally related and those that are non-causally related. This can result in variables being grouped together when they should not be. So it's up to you, the data analyst, to think about the possible types of relationship among the variables and not just let the software make the decisions. So the software would actually facilitate the computation, but the deeper analysis on the outputs of the software should be based on the thoughts, the logical mind of the data and analyst. How to narrow down the choice of variables? According to Ran and Genolis, way back 2001, the selection of independent and dependent variables should be a function of the research question to which the data analysis is directed. Unless a clear research question is formulated, you will find no answers. It is as simple as that. One approach I usually follow is to draw diagrams of the model. I plan to evaluate before I begin to analyze the data. First, I state what my independent variable is. Then I specify the independent variable and the likely mechanisms by which the independent and dependent variables might be related to each other. As simple as it sounds, it is of paramount importance as it helps me make sense and guide the selection of variables for further analysis. When undertaking factor analysis, think about the variables involved before subjecting a set of variables to factor analysis. You should have some idea of what they might have in common. You should make some attempt to include variables that make sense together. You should also avoid including variables where any correlation is more likely due to causal relationship than to the variables having something in common at the conceptual level. So here's an example of factor analysis being applied into a thesis. It's actually the thesis of my advisee entitled Mathematics Teachers' Extent of Making Innovation in the Division of Dumaguete City, an exploratory factor analysis. It's actually a thesis presented to the faculty of the graduate school, Negros Oriental State University, Dumaguete City, in partial fulfillment of the requirements for the degree Master of Arts in Mathematics Teaching by Arturo O. Macias Jr. And I'm his advisor. So let me go directly to the statement of the problem. So his thesis has a total of 4 specific problems. And problem number 3, what are the latent factors underpinning the teacher's innovation in mathematics teaching, which can be identified using exploratory factor analysis? So this actually the specific statement of the problem that calls for factor analysis. So let me go directly to the presentation of his data about problem number 3. So what is being used in his thesis is exploratory factor analysis. So it's here, exploratory factor analysis. So the data collected for problem number 3 is presented in here. It's here, colored in yellow, highlighted in yellow. Perception of the respondents in the extent of innovation of mathematics teaching variables. So rating the items in 4 predetermined factors. So my advice is conceptualize 4 predetermined factors. So the first one, factor 1, the predetermined factor. 1, teaching strategies and lessons. And these are composed of Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8, Q9, and then Q10. So Q1, I encourage students to discuss their mathematical ideas in groups with a member who is good in mathematics. So forth and so on up to Q10, I use games and other tools to link other subjects fields in my mathematics discussion. So all of these 10 items belong to factor 1. And factor 1 is being labeled as teaching strategies and lessons. And you have to take note na factor 1 is actually a predetermined factor by the researcher. Factor 2 is found in table 5. Factor 2, teaching materials and environments. An environment. So we have Q11, Q12, Q13, Q14, Q15, Q16, Q17, and Q18. So it starts from, I use PowerPoint presentation or television in my mathematics teaching. Q12, I give my students assignment to enhance learning. So forth and so on up to Q18. I prepare worksheets and drill sheets frequently. So all of these items belong to factor 2, teaching materials and environment. You have to remember that factor 2 is a predetermined factor made by the research. Next is factor 3, found in table 6, teacher's enhancement. So it is composed of Q19, Q20, Q21, Q22, Q23, then Q24. I joined seminars and trainings about mathematics teaching for Q19. Q20, I make sure that I read more about techniques in teaching the subject. So forth and so on up to Q24. I look for opportunities to know more or ask questions about how to bring new ideas into my mathematics class. So Q19 up to Q24 belong to factor 3, which is being labeled as teacher's enhancement. And still, you have to remember that factor 3 is being predetermined by the researcher himself. Next is factor 4, teacher's attitude as presented in table 7. So Q25, Q26, Q27, Q28, Q29, Q30, Q31, Q32, Q33. So Q25, whatever mathematics innovation is introduced, I will continue to teach in the old way. Q26, I am open to changes in the system and easily adapts with it. So forth and so on up to Q33. I depend mainly on my knowledge and skills when I am teaching mathematics. So Q25 up to Q33 are items that belong to factor 4, teacher's attitude. And you have to remember that factor 4 labeled as teacher's attitude are being predetermined by the researcher himself. So we have factor 1, factor 2, factor 3, and factor 4 are being predetermined by the researcher himself. So let me go back to factor 1. So we have here perception of the respondents in the extent of innovation of mathematics teaching variables. So the respondents rated the items in the 4 predetermined factors. What are those predetermined factors? Factor 1, teaching strategies and lessons. Factor 2, teaching materials and environment. Factor 3, found in Table 6, teacher's enhancement. And factor 4, found in Table 7, teacher's attitude. So all of the 4 are actually predetermined factors. So my advisee made use of exploratory factor analysis. So the mean and standard deviations of all the 33 items as illustrated in tables 4 to 7 is the first part of the test. Item number Q25, even with small mean, was retained because it affects the other items. As the objectivity of this study, R-type factor analysis had applied to the correlation matrix of the variables. So we look at into exploratory factor analysis. So looking into the principal component analysis as found in table 8. So we have factors named. So we have constructivism, then followed by positive teaching attitude, followed by designing teaching materials, then stimulating strategies. So if you remember the 4, so we have to look back the 4 predetermined factors, teaching strategies and lessons. We have teaching materials and environment. Then we have teacher's enhancement. And the last one is all about teacher's attitude. And through exploratory factor analysis, using principal component analysis, so the factors name are being changed into constructivism, then positive teaching attitude, designing teaching materials, and then stimulating strategies. So if you look at constructivism, it is actually composed of Q26, Q27, Q28, and then Q29. So what are these items? I am open to changes in the system and easily adapts with it. I accept students' unexpected responses to a question about a mathematics problem and cater to it. I am happy for students to challenge incorrect mathematical expressions on the blackboard that have been made with or without intent. Q29, I encourage students to explain their own strategies of mathematical solutions or methods to the class. And if we look at the factor loading 0.813, 0.08, 0.750, 0.660. So if we consider at least 0.4 as our standard, then all of these factor loadings are actually meeting that standard. And my advisee term these statements, Q26, Q27, Q28, Q29 as constructivism. So how did my advisee came up with constructivism? Of course, he did an intensive research on how to call Q26, Q27, Q28, then Q29. Aside from conducting review of related literature, he consulted also experts on whether constructivism would fit to Q26, Q27, Q28, and then Q29. And validations have been conducted by different experts on whether these different items, Q26, Q27, Q28, then Q29, can be called as constructivism. The second factor is all about positive teaching attitude. And this one is composed of Q22, we have Q23, Q24, and the factor loadings, we have 0.836, 0.804, then 0.732, which actually meet the standard of at least 0.4 factor loading. And again, my advisee did an intensive review of related literature on how to call Q22, Q23, and Q24. And finally, he called it positive teaching attitude. So Q22, I asked other teachers' opinion and learned from their experiences. Q23, I used different form of genre to learn mathematics more. Q24, I look for opportunities to know more or ask questions about how to bring new ideas into my mathematics classroom. And of course, different experts have been consulted also. And the term positive teaching attitude has been validated by different experts, aside from intensive readings on how to call these different statements. The next term is designing teaching materials, and is composed of Q14, Q15, then Q16. So what are these? Q14, I use mathematical tools such as geoboard, compass, and protractor in my teaching. I prepare visual aids frequently. Q16, I design bulletin boards with math-related concepts. The factor loading, 0.785, 0.730, 0.729. And all of these are actually greater than 0.4. 0.4 as the point of reference for acceptable loadings. So again, my advisee did an intensive research on how to call these statements from Q14, Q15 to Q16. And finally, he came up with the term designing teaching materials. And of course, this term has been validated by experts. The last one is stimulating strategies. And this one is composed of Q3, Q5, then Q10. I encourage students to work on real-life related problems by themselves. Q5, I use thought-provoking problems in my lesson. Q10, I use games and other tools to link other subjects, fields in my mathematics discussion. Factor loading, 0.785, 0.730, 0.729. A factor loading greater than 0.4. So 0.4 is our point of reference as acceptable factor loading. So again, my advisee, Mr. Macias, did an intensive research and then validated this term by panel of experts on whether stimulating strategies would be the right term for Q3, Q5, and Q10. So initially, the predetermined factors were named as teaching strategies and lessons, teaching materials and environment, teachers enhancement, and teaching attitude. Through factor analysis, those different factors are being named, and they are being called constructivism, positive teaching attitude, designing teaching materials, and stimulating strategies. If you count the number of factors, actually the same. The first one, 1, 2, 3, and 4. After the factor analysis, we have 1, 2, 3, and 4 also. But if you notice, the different statements that belong to each of the 4 new factors are being reduced. If you notice, constructivism, factor 1 is composed only of 1, 2, 3, and then 4. And then positive teaching attitude, 1, 2, 3. And then designing teaching materials, we have 1, 2, and then 3. Stimulating strategies, 1, 2, and then 3. So overall, if we're going to count the items that belong to the new naming of the factors, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 items being distributed to stimulating strategies, designing teaching materials, positive teaching attitude, and constructivism. But if you look at the predetermined factors, so we have factor 1 composed of 10, then we have 11 to 18 for factor 2. Then from question 19 to Q24 factor 3. And from Q25 to Q33 factor 4. So originally there were 33. But after factor analysis, the remaining statements is now 13. So 33, after the factor analysis, we have a total of 13. I repeat, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So from 33, it is being reduced to 13 statements. And still the number of factors 4, we have constructivism, positive teaching attitude, designing teaching materials, stimulating strategies 4. But each is composed of fewer sub-items. And that's why we classify factor analysis as a way of reducing many variables into smaller number or fewer number of variables. But I'd like to have this thing, that the naming of the new factors would be so difficult. This is actually a difficult part because you have to think logically on what would be the exact term, the appropriate term, the logical term for Q26, Q27, Q28, then Q29. Positive teaching attitude. It took time for my advisee to come up with this term, in which this is actually a term for Q22, Q23, and Q24. For Q14, Q15, Q16, the term is designing teaching materials. It's not actually done overnight, but as I mentioned earlier, an intensive research is being done how to call these terms. So with Q3, Q5, and Q10 being called as stimulating strategies. So the naming of the new factors would be classified also as a difficult part because you have to validate that one through different literature and according to some of the logical thoughts of experts. So that's actually one of the examples that I would like to share in this webinar about factor analysis in a thesis. So let me share another one. So factor analysis being used in validation. So I got this from a journal, and the title is One Size Doesn't Fit All, using factor analysis to gather validity evidence when using surveys in your research. So factor analysis is being used for validation of a certain instrument. So let me go directly to table 1. So table 1 is actually talking about types of validity evidence to consider when validating an instrument according to standards for educational psychological testing association. And it's actually part of the research methodology. When an instrument is actually being developed by the researcher, a researcher-made instrument, you need to validate the instrument. And one of the things that you are going to consider in validating the researcher-made instrument is through the use of factor analysis. But let me review about the different types of validity. So we have evidence-based on test content, evidence-based on response process, evidence-based on internal structure, evidence-based on relations to other variables, evidence-based on the consequences of testing. So let me define as being reflected in this table. Evidence based on test content, analysis of the relationship between an instrument's content and the construct it is intended to measure. For evidence based on response process, information on how respondents answer the instrument's items. Evidence based on internal structure, analysis of internal relationships between instrument items and instrument components and how they conform to the intended construct. Evidence based on relation to other variables, analysis of the relationships of instrument scores to variables external to the instrument and to other instruments that measure the same construct or related constructs. So evidence based on the consequences of testing, the extent to which the consequences of the use of the score are congruent with the proposed uses of the instrument. So, example considerations. Does this instrument represent the appropriate aspects of communal goals construct as described by the theoretical framework? Second, is it reasonable to assume that the respondents were motivated and honest when answering the instrument? Did the respondents understand the items as intended by the researcher? Does factor analysis support the relationships between items suggested by the theoretical framework? Can the instrument detect differences in the strength of the communal goal endorsement between women and men that has been found by other instruments? Does the instrument correlate in expected ways with similar and or dissimilar measures? Will the use of the instrument cause by unintended consequences for the respondents? Is the instrument identifying students who need extra resources as intended? So you have to take note that validation of the instrument is very important. If it is poorly validated, it's not scientifically validated, then it would affect the major findings as well as the conclusions of the entire study. So one thing to consider in validating an instrument is to the use of factor analysis as being illustrated in this article. So we have Table 2. Table 2, items included in the Dickman et al. Goal endorsement instrument. So items, we have power up to 23 spiritual rewards. And we have 3-factor solution, 4-factor solution, 5-factor solution. So I will not be discussing on how these values are being determined, are being calculated. The next webinar series will be talking about the computations. Let me look at into the original items from item 1 up to item 23. And how are we going to classify, to cluster these different items? So looking into factor analysis. If you look at into exploratory factor analysis in a theoretical perspective, so we have factor 1, factor 2. So we have composed of item 1, item 2, item 3, item 4. And for factor 2, we also have item 8, item 7, item 6, item 5, item 4, item 3, item 2, and item 1. It's actually a figure that shows exploratory factor analysis. In terms of confirmatory factor analysis, you would notice now we have factor 1 and factor 2. And the components of factor 1 are actually different from the components of factor 1. So item 1, item 2, item 3, item 4 belong to factor 1. Item 5, item 6, item 7, item 8 belong to factor 2. So there is what we call independence between factor 1 and factor 2. This one, in the exploratory factor analysis, factor 1 and factor 2, you will notice that there are common between factor 1 and factor 2. So looking into factor analysis, applying factor analysis, we come up with this. So table 3, still we have item 1 to item 23. So if we look at table 2, let me go back to table 2. So we have still the same number of items, item 1 to item 23. But if you look at table 3 is actually having the specific clustering. We have 1, 0.84, 0.80, 0.80, 0.75, 0.74, then 0.50. Then we have factor 2, 0.75, 0.60, 0.56, 0.76, 0.55. We have a smaller loading 0.20. We have 0.65, 0.69, 0.50, 0.55 for number 3. Column 4, 0.94, 0.53. And column 5, we have 0.81, 0.55, then 0.40. So it is being clarified in here that the coefficients less than 0.2 are not being shown in the table. So if you notice, all of these coefficients are greater than 0.20 or equal to 0.20. So we look up into the groupings. So we have here prestige. If you look at this, prestige, autonomy, competency, service, and then connection. So item 1, 2, 5, 8, and 11, prestige. So if you look at 1, 2, 5, 8, and then 11. All of these factor loadings are greater than 0.4. And we have this in this diagram, 1, 2, 5, 8, and 11. And all of these items are being named as prestige. So if you look at the term prestige, we have power, recognition, then self-promotion, status, then financial rewards. So the researcher is able to come up with the term prestige. But of course, it's not actually an easy way of determining the term for this is actually prestige. It has to be researched, it has to be validated by experts. Second is on autonomy, and it is composed of 6, 7, 9, and 12. 6, 7, 9, and 12. So that's number 6, number 7, number 9, and number 12. Number 6, independence. Number 7, individualism. The number 9, focus on the self. Number 12, self-direction, 0.55. And if you look at these different items, they can be classified as autonomy. And of course, it's actually being researched by the author and being validated also by experts and even through the use of review of related literature. The next is competency. We have 3, 10, and 13. So if you look at 3, 10, and 13, so we have number 3, achievement, number 10, success, and number 10, demonstrating skills or competence, 0.40. So all of these are actually being named as competency. And factor loadings, we have greater than 0.4, 0.74, 0.67, 0.56. Then the next factor is service. So we have 15, 16, 17, 20, and 21. Service. So helping others, serving humanity, serving community, attending to others, caring for others, spiritual rewards. So all of those are actually termed as service. The name of the factor is service. And it's actually very logical that these items are being labeled as service. Helping others, serving humanity, serving community, attending to others, caring for others, spiritual rewards. It's actually service. And the last name of the factor, connection. It is composed of item 18 and item 19. So we have here 18 and 19. So look at the factor loadings, 18.94. It's actually working with people and then connecting with others, 0.53. And that's actually connection. It's actually a right term, no? Connection. If you look at the statements 18 and 19, working with people and connection with others. So the right term is connection. Of course, there are times that you can think easily about the term based on the statements provided. And we have to think that the term being used for the new factor's name should be very logical, and they actually justify and actually correlate with the different items in the cluster. So looking into the final one, table 4, propose 5-factor solution. So we have service, helping others, serving humanity, serving community, attending to others, caring for others, spiritual rewards, prestige, status, power, recognition, self-promotion, financial rewards, autonomy, individualism, independence, self-direction, focus on the self, connection, working with people, connection with others, competency, achievement, success, and then competence. So these are actually the new names of the factors. So if you consider from the very beginning, we have the contents of the instrument. So the instrument is composed of 23 items, number 1, number 2, up to number 23. But if you look at table 2, there are no specific clustering of the different items. But looking at factor analysis, we are able to, the author of this article is able to come up with the clustering of the different items. And what are those different clusters? So we have service, prestige, autonomy, connection, and competency. So how many items? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20 are included in the final. Originally, there are 23 as found in table 2. But now in table 4, it's 20. And these 20 are being clustered according to service, prestige, autonomy, connection, and then competency. So those are actually some very common examples that I can actually talk about in this webinar about the basic concepts of factor analysis and common examples of factor analysis. So thank you very much. Again, this is Dr. Craig and Refugio from Negros Oriental State University, Main Campus 1, and I'm the Vice President for Research and Extension of the Basic Education Math Teacher Society. Thank you for listening.